Hello and welcome to this lecture. We've done all the preparations that we need to start looking at eigenvalues and eigenvectors. So let's begin. So a quick recall of what we knew before about linear dependence, independence, invertible linear transformation. Just a very quick recall because we'll use some of these ideas when we define eigenvalues. So first thing you can want to recall is in R2, two vectors may be linearly dependent, linearly independent. But once you have three vectors, they will definitely be linearly dependent, right? You cannot have three linearly independent directions in R2, so that you can see that. It's one fact I'm quickly recalling for you. And when is a linear transformation T invertible, and linear operator T is invertible if the rank is full, right? So in terms of matrices, the columns should be linearly independent or the rows should be linearly independent for a linear transformation to be invertible. And it's also the same as saying the null of this transformation is 0, right? So, I mean, we're talking about operators here. So, the null of the operator is 0, then it becomes the same as rank being 2, range being the entire plane, and it being invertible. Okay, here is a terminology that we have not introduced so far, but this is a common terminology. If a linear transformation is not invertible, it is said to be singular. It's just a name. Basically, if the null space is not exactly the origin alone, it has something non-zero in it, then the linear transformation is not invertible, right? Anything, if the null has something, then it is not full rank, right? So, it is not invertible, and in that case, the linear transformation is said to be singular. The matrix is also called singular, right? So, this is a terminology we will use. So, notice here that this is a very important and simple fact. If T is singular, it's not invertible, and there is a non-zero vector in the null space, right? So, T times V is 0 for a non-zero. Okay. Quick recollection, we will recall these things quite often in the proofs that we do going forward. Okay, so we are ready to define the eigenvalue. Okay, so the eigenvalue is basically a complex number, lambda. It is said to be an eigenvalue of a linear operator T. Notice what I'm doing. I have a linear operator T, and then the matrix with respect to say canonical basis is A11, A12, A21, A22. And a complex number lambda is said to be an eigenvalue of T if T minus lambda I is singular. Okay, so this is just a definition. We'll define it for now and then think about what it means and all that as we go along. Okay, complex number lambda is said to be an eigenvalue of T if T minus lambda I is singular. Okay, so what does that mean? So T itself is an operator. So T minus lambda I is also an operator. So we saw the algebra of operators, right? So when you do T minus lambda I, it's also another operator. Now, T may be singular, may not be singular, I don't care about that itself. But I want to see if there is a lambda which when you subtract do T minus lambda I, will I be able to make this T minus lambda I singular? Okay, what does that mean if it's singular and all that? We'll see soon enough. But this is the definition for an eigenvalue of a linear transformation or linear operator. Okay, so we'll also say that lambda is an eigenvalue of the matrix M of T. Okay. So, it turns out the eigenvalue depends only on the operator and not on the basis with which matrix is taken and all that. We will see that later. So, this definition is also okay. You can call it an eigenvalue of the matrix also. Okay. So, notice what happens when you do T minus lambda I. When you do minus lambda I to M of T, you are going to subtract lambda from the diagonal. Okay. So, that is how you do try and compute eigenvalues. How do you find eigenvalues? How do you know that such complex numbers exist? I mean, of course, when I say complex number, real numbers are also included in it. Okay, eigenvalues can be real also, need not only be complex. I'm saying complex, but in general, you may have only complex eigenvalues sometimes. Okay, so we'll see that in examples. So how do you find eigenvalues? You use a matrix representation, just like any computation uses matrix representation with linear transformation. Eigenvalue computation also uses a matrix representation. You do this M of T minus lambda I2. So what is I2? I2 is a 2 by 2 identity matrix. So you do lambda times I2 and then you subtract it from M of T. That's the same as, that's the matrix for T minus lambda I, right? What is the matrix of T? Matrix of T is M of T. What is the matrix of I? Matrix of the identity transform is I2, 2 by 2 identity matrix. And then T minus lambda I is M of T minus lambda I2. Okay, the same operations you did for the operator goes for the matrix as well. So when you do minus lambda I2, I2 has 1 in the diagonal elements and 0 in the off diagonal elements. So you can see that this is exactly this matrix. So A11 has a lambda subtraction, A22 has a lambda subtraction. These two elements are by themselves. Okay. and I want to find lambda such that this matrix is singular. Okay. Now, what do I know about singular? I mean, it means that this column and this column have to be linearly dependent, right? They cannot be linearly independent. How do I make these two columns linearly dependent? Two columns being linearly dependent, I know exactly what the condition is, right? This cross products must be equal, right? These two cross products must be equal. The two columns have to be linearly dependent, which means these two cross products have to be equal, and you get a quadratic equation. That's it. Okay. So, finding eigenvalues for a 2 by 2 matrix or a linear transform from R2 to R2 is quite easy, because they end up being solutions of the quadratic equation. So, you see why quadratic equations can have complex roots, no? So, that is why you need to have generally complex number as the lambda here, eigenvalue, but it could be real also. There are many quadratic equations which have real roots, you know that. So, this could be real also. Okay. So, this is the definition of the eigenvalue. It is a very simple basic definition, and you can see how to use it, right. So, we are going to see how to use it next. So, we will give a whole bunch of examples. So, let us look at this examples and see, go through, and maybe one or two I will show you, and then go through and illustrate how these answers come about. Okay. So, the first example is 1.5.51. What will be the quadratic equation? 1 minus lambda times 1 minus lambda minus 0.5 into 0.5 equals 0.5 into 0.5, right. So, this is this product after the lambda subtraction has to be the same. So, this if you solve, you can solve the quadratic equation, you are going to get lambdas 0.5 and 1.5. These are the roots. So, the eigenvalues of this matrix are 0.5 and 1.5. That is it. So, this showed you what to do, and you can repeat it for every other case. Okay. So, I am not going to do the calculation. I will tell you what the answer will be. Okay. You can see and repeat it. You should do it yourself, convince yourself of this answer. For this matrix, the eigenvalues will be complex. Okay. You can see, 1 minus lambda whole squared equals minus 1. So, the square on the left hand side has to be negative. So, that is not going to really happen for real numbers. So, it will become complex. Okay. So, this ends up being having complex roots. So, you will get two complex conjugate eigenvalues. Okay. Calculate them. So, this one is a very interesting matrix. If you do this, notice what happens. 1 minus lambda whole squared equals 0, right. 1 minus lambda whole square equals 0. So, you will get repeated roots. There are two roots, but both are the same, lambda equals 1 comma 1. Okay. So, that is an interesting thing to see. So, in general, you can see if one of the off diagonal elements is 0, okay, if the matrix is upper triangular or lower triangular and the off diagonal elements is 0, then the eigenvalues will just become what is there on the diagonal. Okay. So, think about why that is true. So, 1 minus lambda into 1 minus lambda, whatever is on the diagonal will be the eigenvalue, easy to see. So, here is an example of a complex valued matrix. You can go through and plug it in and solve the quadratic equation. You should know how to take a square root of a complex number. You can go to the polar representation and then take the square root and then come back to rectangular if you like. So, that way you can compute it. So, this anyway, modern calculators will have all these built in. So, you can do this computation. So, finding eigenvalues is a routine operation. It is for 2 by 2 matrices. Just have to solve a quadratic equation. Okay. Okay. So, here is a quick proof for the existence of eigenvalues. This is an alternative proof. Okay. So, we know for 2 by 2 linear operators from R2 to R2 or 2 by 2 matrices, eigenvalues clearly exist. They are the solutions of a quadratic equation. There is no problem there. But here is a quick alternative proof. I am going to go through this very quickly, because this proof will help us later on when we want to generalize. Okay. So, here is the idea. Okay. The basic idea is this. When you have a non-zero vector in R2, and then you look at these three vectors, v, t of v and t square of v. Okay. So, what happens here is there are three vectors in R2. So, what will happen if you have three vectors in R2? They have to be linearly dependent, which means there are real numbers a, b, c, not all of which are 0, such that a t square v plus b t v plus c I v equals 0. So, I put the I there, identity, just to emphasize that this is like an operator acting on a vector type thing. Okay. So, I is the identity operator. So, when various things can happen here, this is like a quadratic equation in the operators, right. So, various things may happen here, maybe a is 0. Okay. If A is 0, B 0 is not possible. Okay, this cannot happen. If A and B are both 0, then C times V is 0, but then C has to be non-zero, because A, B, C are not all 0, and then V is also non-zero. That is a contradiction. So it won't happen. B equal to 0 won't happen. If B is not 0, then you can divide by B, right? A became 0, you divide by B, you get, and then take sort of V common out and then make it an operator equation, and you see this T plus C by Bi, the whole operator, think of this as an operator acting on V. Okay, so this is the same as TV plus C by BV, right? It's the same as this, but I've rewritten like this. So you get some equation like this. So some T plus some lambda times I V equals 0. Okay, so you notice here, and V is non-zero, right? So you have a matrix here which is of the form T minus lambda I, and it is singular, right? Because it's got a non-zero vector V equal to 0. Okay. So here clearly if A is 0, you have an eigenvalue, right? You have T plus T minus lambda I being singular. So that is eigenvalue. Okay. Now what happens if A is not equal to 0? You have this operator equation T squared plus B by A T plus C by A I V equals 0. But this is not of the form T minus lambda I. How do I make this into T minus lambda I? I have to appeal to quadratic equations. So let me appeal to quadratic equations here. How do I simplify this guy? You take the quadratic polynomial, so you replace this t with some x, okay, some variable x, and think of this as the quadratic polynomial x squared plus b by ax plus c by a. So this will have two roots, alpha, beta. Both could be real or both could be complex, we know that. Now we know that the sum of the two roots is minus b by a, and the product of the two roots is c by a. So that x squared plus bx plus c by a becomes x minus alpha into x minus beta. So what happens? Once you have this alpha and beta solutions, you can go back to your operator here, the quadratic operator here, and use this fact in a very nice way like this. So let me look at very smartly t minus alpha I times t minus beta I. Okay. Notice what will happen to t minus alpha I into t minus beta I. This is like operator algebra. You have to just multiply, add, etc. You're going to get this. You're going to get this, right? So you can see that the terms add ti and it are the same. You get this. Now alpha plus beta is minus b by a, alpha beta is c by a, you get this guy. Okay. So this equation here, the quadratic operator equation, becomes the product of two linear sort of terms, right? This t minus alpha I, t minus beta I. Okay. So you get t minus alpha I times t minus beta I, v equals 0. Okay. So I'm getting somewhere, right? I'm getting these operators of the form t minus lambda I, right, even when a is not 0, even when you have a quadratic, because I am able to factor the quadratic into two linear terms. So I get a t minus lambda I type situation. So now how do I exploit this? So here is the way to think about it. So if you put all together, if you have for a non-zero v, I know this is true. Now if a is 0, I already get a t minus lambda I being singular, right? This matrix times v is 0, v is in the null space, it's not 0, so this is singular. Now, if a is not equal to 0, you have t minus alpha I into t minus beta I v equal to 0, and alpha beta are roots of this equation. Now, the claim is either t minus alpha I or t minus beta I have to be singular for this to be true. Okay, how do you prove it? You prove by contradiction. Okay, if both are invertible, then null of this product will be 0, right? We have seen that if both both two matrices are invertible or two operators are invertible, the product is also invertible and the null space is 0. But then you have a non-zero vector v which multiplies this operator and gives 0. So clearly one of these two guys will have to be singular. I don't know which one, but I don't care, right? Whatever happens, I know in either case there exists a complex number lambda such that null of t minus lambda is not equal to 0 or t minus lambda is singular. Okay. Notice in this proof I didn't use any matrices, right? So in the previous version when we found the eigenvalue, I used the property of the matrix, right? The two columns being linearly dependent means the cross products have to be equal, right? So that property I used directly to get to the equation. Now here I didn't use it, I was just using this operator algebra and giving you a proof. So that's the power of this proof. It's a slightly abstract proof right now. It may not be very immediately obvious to you why this is useful, but when we extend it, these kind of proofs are very, very useful. Okay. So that concludes the proof for existence of eigenvalues. That concludes this short lecture. We'll continue in the next one. Thank you.